So this is a presentation about a type of problem in Calculus 1 that for some students is quite confusing. It's a graph matching problem in which one has to match the graph of a function and its derivative. And in more complicated versions, sometimes you see 3 or more graphs in the same coordinate system, in which, let's say if you have 3 graphs in which you have to identify which graph stands for the original function, which graph is for the first derivative, and which graph is for the second derivative. So let's focus on the most basic case when you have 2 graphs, right? So you have the original function, and let's say you have to pick among 4 choices, which graph is the one corresponding to the derivative of the original function. I would actually suggest that the best way to learn this is to actually try to sketch by hand the derivative, the derivative function of the original function you see, because then it's going to be pretty clear among the choices you see in the textbook problem which function you should pick for the derivative. It all relies on clear understanding the meaning of the derivative with respect to the graph of a function. I think that's the key problem in the cases where this problem cause confusion. So remember, the derivative among its various meanings, one of the most immediate graphical interpretation, if you want, is that it denotes the slope of the tangent line to the graph of a function. So if you look at the graph of the original function, the value of the derivative, it's not the y-coordinate of the point on the graph, but it is the value of the tangent, of the slope of the tangent at that point. So in this first drawing here that I want to show here, basically at any point on the domain of a function, if one wants to visualize how big or small the derivative is, or whether it is positive or negative, you should basically associate it with a line which is either inclined from the left to right or up, right? Either goes down or goes up from left to right. So to put it differently, if the tangent line is very steep like that, let me actually use a different tool here. So let's use actually a straight line. So if the tangent line is very steep and going down like this, that signifies a large negative derivative. Let's say this is minus 100 or something. If the tangent line is still going down but less steep, it's still negative but not as large. Let's say this is like minus 50. Let's say this one here is, I don't know, like minus 1, minus 0.05, so very, very close to 0, but still negative. So as long as it goes down, the tangent line to the graph, it still signifies a negative derivative. So once again, a large negative derivative, a tiny negative derivative, almost nearly horizontal, right? And of course, if the tangent line is completely horizontal, that means the derivative in that case is going to be 0. Furthermore, on the positive side, if the line seems to go up from left to right, that means a positive derivative. So this, for example, let's say it could be, 0.02, 0.03, I don't know, but small but still positive. And obviously, if you have a very steep tangent line that goes up, again, from left to right on the domain, that's a large positive derivative. So visually, you should basically imagine, or you should draw in your mind this tangent. So you look at the graph of a function and figure out whether the derivative is positive or negative and how large it is, how large negative as a number is and how large positive number. So that being said, let's start with the function and let's try underneath in the drawing area below here to kind of give a rough sketch of the derivative function. So obviously we're going to choose, for simplicity, a function which is differentiable at all points. Okay, so this is a polynomial function. Let's let Maple know what it is. X plus 2, x squared times x minus 3. And let's plot it. And we're going to have to play a little bit with the coordinate systems, because obviously we need to see what happens around the important points where the function crosses the x-axis. So let's choose -4 and 4, the x range, and the y range -20 and 20. Okay, so we see most of the features here that we are interested in. Okay, so let's make it a little bit smaller, not by much, just a tiny little bit smaller, so that I can fit, so we can visualize a little bit the drawing area below. And let's see what we'll do if we want to sketch the derivative of this function. Let me see if we can make it slightly better here. So let's say a little bit wider, just like that. So imagine this is your piece of paper, and then, you know, using a pencil. It's not going to be that great with the drawing tool in Maple, but let's say you sketch a coordinate system right underneath the graph of the original function, and you try to sketch the x and the y coordinates. Okay, so that's the key thing now. Grab your pencil. Now, of course, in my case, I'm going to just grab the pencil tool from Maple. And let's see if I want to sketch the f prime of x. So again, the goal in this area is to sketch, roughly speaking, the graph of f prime of x. So above here is the graph of the function f of x. We want to sketch the graph of f prime of x. And at this point, imagine you follow the tangent lines. So at each point on the graph, you sketch the tangent and you ask yourself whether it goes down or up and how steep it is. So it should be pretty obvious that if we start at this point, this is going to be a very steep going down slope. So the value of the slope is a large negative number. Large negative number. So for example, corresponding to the point -2.5, probably f prime of x has a value of the derivative somewhere here below the x-axis. So it should start from a pretty low value, large negative value. And what happens as it goes from left to right, as you move along the graph? Well, that negative value keeps on getting less steep, so less negative, right? So let's say this is -50, then it's -40, -30, keeps on leveling off, and it gets close to a point right here where the tangent is horizontal. So the derivative is 0. So the value of f prime of x up until this point will go up from a very large negative number all the way up to 0. So right underneath this point, if you put here a dot here so you can mark it down, I don't know what that point is, it's somewhere in between -3 and -1. But anyway, up until that point, f prime of x should be looking like this. Going from negative, you don't have to be very precise in terms of the shape, but roughly speaking, it's going to be going from a large negative value on the y-axis all the way up to 0. And this point here, where it's going to be 0, again, it corresponds to this point, which has a horizontal tangent. Again, a horizontal tangent means the derivative is 0. Now, let's pay attention to what happens between this point and 0. Now, it should be pretty obvious that tangents are all positive, right? I mean, the graph goes up. Any tangent line is going to be going up from left to right. But notice it goes from a small value, from 0. It keeps on increasing up until this point, and then it levels off again towards 0. So again, it gets steeper and steeper and steeper, and then less and less and less and less steep, but still positive. So again, between this point and 0, all tangents are positive, or derivatives are positive, in other words. But they increase and then they level off again to 0. So between this point and 0, the derivative should be, roughly speaking, like this. It goes up in the value, the slope value, and then it levels off. Again, it's worth mentioning once again, what you see here when I draw with a pencil is not the value of the function. It is the value of the derivative. So I'm trying to essentially look at the values of the slope. F prime of x will give you the values of the slope of the original function. And at this point, maybe you should pause and try to guess what happens between this point and the level of point here, when it's again horizontal. And I hope it's clear that it's gonna be actually symmetric to this, right? You have negative slopes, that should be pretty obvious. All slopes are negative. But again, they start from something close to zero, so it starts from zero and then gets more and more steep on the negative side, right? So I mean, it gets steep from left to right and gets larger and larger negative. So that means steeper and steeper and on the negative side, and then it levels off up to zero. So again, between the point 0 and whatever this point is, right here, the derivative should make this type of shape. Steeper and steeper, that means more and more negative, and then less and less steep, but still on the negative side. And then finally, from this point to infinity, kind of like this, but on the positive side. The derivative gets steeper and steeper on the positive side, so the values should keep on increasing like that. So roughly speaking, this is how the derivative of this function should look like. Again, pause the video a little bit if you want to retrace these arguments, and when you're ready, you can continue. And now let's confirm with Maple that I was right with this type of shape. So f prime of x, I enter f prime of x in the math mode, so that's the derivative of the function. If you want, we can let Maple simplify it a little bit so it looks better. And let's plot it in precisely the same coordinate system. So we can superimpose it with f later on. So let's see, the coordinate system was -4 and 4 for x, and I remember that y was -20 and 20. And to not confuse it with the original function, let's change the color. So the derivative will be blue, right? The graph of the derivative will be blue, and I should be able to scroll up and drop this derivative over the same graph. Okay, so as you can see, I was pretty, the shape is essentially what we predicted it. So this is what you should do before you actually choose. Try to figure out the values by essentially drawing the derivative below the original function. And let's again notice something very important. Let me make this a little bit bigger. Notice that the point where f prime of x, the blue stuff, crosses the x-axis is exactly the same point where the horizontal tangent is, the tangent is horizontal. Horizontal tangent means derivative 0. Steep from left going down means negative. Going up, from left to right, that means positive. So obviously horizontal tangent means the derivative is 0. So it's not a surprise that the points where f prime is 0 are identical to the points where the derivative is equal to 0. Where the original function has a horizontal tangent. Same thing here, as you can see, around 0 and around this point. So this, we have a horizontal tangent, and at the same x-coordinate, the derivative is 0. What that x point is, that's a different story. That you will have to compute those if you can. So the zeros of the derivatives, of course, are not the same as the 0 of the original function. Although they could be, as you can see in this case, in the case of x equals 0. So that happens to be the 0 over the original function, but it is also the 0 of the derivative, because it also happens that the tangent is horizontal at that point. So I hope that helps in dealing with these problems when you have to match. Above all, the most important advice, which again, if you forget this, it can still be confusing. When you look at the derivative, you do not look at the values of the original function. You look at the values of the slopes of the tangents to the original function. So I hope that helps, and that's it for today.